Good morning, sir.
Good morning, sir.
So today we will start basic text preprocessing. Whatever the text preprocessing we will be needed for our NLP model, that we will see. So are you aware about tokens? What are the tokens? So tokens are the part of like a smaller part of our text. So and why that tokens are more important, because you might know that ChatGPT and other commercial LLMs, they will be they will paid by tokens. They will charge you by tokens. How many tokens you are using? By that they will charge. So knowing this, how many tokens will be in our word and sentence is more important. So today, yeah, is my screen visible?
Yes, sir.
So first thing we will see today is a tokenization. Tokenization. So we saw yesterday. So first we will be getting corpus, and from this corpus we have to create vocabulary. So what is corpus and what is vocabulary? Can anyone tell?
Corpus means complete data set, and vocabulary means unique words from that corpus.
Yes. So from that corpus we need to get whatever the unique words are there, and so that we can convert that unique words into vector representation so that our model can understand. This becomes much more important to get correct number of tokens so that we can efficiently convert it into its vector representation. So token is referred to the smaller part of text, whatever the text we are getting, how much small we can make it without like losing more information. If we convert each text into individual characters, so it not be significant, right? So if we have only t, it doesn't mean anything. We cannot convert it into significant vector so that it will be used for like tokenization also, and any other word like team. So we cannot convert that t into some significant vector so that we will get vector representation for both. So we have to convert it into words, such a words like it we can get the significant vector representation. So there are different methods for tokenization. So first we will like one string we will give, and we will perform the different tokenization method on this string. We will get will cost some dollar, and we will give some again dot. And something will give. So this is the string we have to tokenize the string. So first thing we like what comes to mind while splitting the string, you might have heard about the string method split, right? What it will do?
Divide the text into the individual
Into
words.
list.
Yes, based on white spaces, it will split. Here it has make ice cream as one token, will cost. It has converted like quite good, but one problem with this split method is here it is combining like this thanks. It is combining with dot. If we get like each this one, whatever the punctuation we have, if we convert, if we are appending it with our text, it will our vocabulary will be much more. So what will happen? This thanks with dot will be treated as unique word. So this we don't want, right? So for that, NLTK library provides different type of tokens. Like one of them is like word punct tokenize. What it will do? It will use regular expressions to split based on white space and punctuations. So we will see that word punct tokenization. Word. Yes, this one. And then we will create one. So now what it is doing, it is not only splitting just simply based on white spaces, it is also using whatever the character, these punctuations we have, right? So here it split ice and cream separately. Dollar also it splitted. But here problem you can see, we don't want ice cream as a separate, right? So for that, we need to handle this also correctly. So, and some of the models are there, like Transformer Excel. Transformer Excel. That model uses this tokenizer. Like it will split based on spaces and punctuations. But is this correct method? Like we are splitting this ice cream separately. Because of that, what is happening? Its vocabulary become too large. For this model, vocabulary is more than 2,50,000. Comparing to the BERT only has a vocabulary of 10,000. So what will happen if our vocabulary is too large? What do you think? What will happen?
It will take more memory, time, and resources to compute.
Yes, correct. It will take more space, like and for calculation, for inference also, it will take more time. So we don't want vocabulary that much of size, right? So then again, two more tokenizers are provided by this NLTK library. That one, word tokenization and sentence tokenization. That you might have heard, and also you might have used somewhere. Word tokenize and send tokenize. So what this send tokenize and word tokenize will do? This send tokenize will split whatever the paragraph we have to the sentences. And word tokenize, what it will do? It will split each word by word. So if you want to see how this word tokenizer work, we will simply give our string here. Okay. For this, we need to download punct, and this one we will download. So in NLTK, they have like different types of rules or something that will be stored in punct and other libraries also, WordNet, that we have to download separately. Now it splitted it, right? Ice cream didn't split it like differently, and also thanks don't include that dot, right? So this is quite better, but still it has some problem. So, and sentence tokenizer will be used for converting sentence separately. So sentence transformer simply will split based on character, like this one, punctuations. either dot or question mark or exclamatory mark. Here it is splitting into 3 different sentences. This one, thanks and something. So, but here also it is appending this thanks like dot. Here also it is appending. So what is problem with this kind of tokenization? Like these are not giving us like whatever the good result, and they might cause some extra word in our vocabulary. Like here this thanks, and here this dollar, everything is splitted separately, right? So one more is there, that is white space tokenizer. What it will do, simply based on whatever our split method was doing, the same thing it will do. So this white space tokenizer we will use. For this we have to create first object, and then we will use this object dot tokenize our string. So it's splitted simply based on white spaces. So is this the correct way, like efficient way or best way to create vocabulary? Each tokenization will give us like some problem it is giving, right? Some like appending dot end of the sentence, something problems are there. So how we can solve this? Either we have to go word by word, but if we go word by word, some problems are coming. Other method is if we go each character like I, C, E. For that also what we saw, like we cannot convert each individual character into meaningful vector representation. So for that, so what we want? We don't want like our vocabulary will be too large, and also we don't want like each individual character too small, so that we cannot convert that into vector representation, right? So what will be better way, like between character to word? So that is subword tokenization, and this subword tokenization is like most important. All the LLMs will be using this subword tokenization, BERT model, GPT model. So how this subword tokenization will work? Consider we have some words like small, smaller, smallest, then tall, taller, tallest. If you do word tokenization, what it will do, it will convert each word into separate token. So 6 tokens will be created. But what subword tokenization will do, it will create tokens like this. First it will create for one small, one for tall, and then hashtag ER and EST. So what it is doing, it is splitting subwords. So from this combination, we can make almost all the word from here. So our both problems got solved. Like our vocabulary won't be too large. And second problem, we got like significant or meaningful unit that we can convert. So these hashes are included, so that we got to know it is part of some other word, right? So what will be here tokenization for this? It will be, if you tokenize this, how it will become? It will become like this: small, then small, and again small, and EST. Is it clear? Any question on this? How this tokenization is happening?
येस
Yeah.
सर हे लॅमिटायझेशन सारखं काम करता काय
नाही नाही. सो हे जे वर्क करते त्याचं वर्किंग आपण पुढे पाहणार आहोत. त्याच्यासाठी डिफरंट मेथड आहे, पण लेमॅटायझेशन सारखं नाही. So there are 3 main type of subword tokenization that one by one we will see. So first one is byte pair encoding. Byte pair encoding. Second one is word piece. Word piece tokenization. And third one is sentence piece. So GPT models use this one, byte pair encoding. BERT model use this one. And this one used by some different model like XLM we have. So each we will see individual one by one, what is working of this one, what is working of word piece and everything. So first we will see byte pair encoding. So actually byte pair encoding first invented as a compression algorithm. What is compression algorithm? Anyone knows? So in compression, what we will try to do, whatever the data we have, we try to squeeze that data into smaller space. Like whatever data, how much, like smaller space, as small as space required. So how that encoding algorithm works, first we will see that, and then we will see how byte pair encoding for tokenization it will work. So for compression, what will happen? Consider you have word, then B, D, A, B, A, C. This is the word. Like we have this word, and we have to compress this. Like for saving this, how many bytes it will be required? Currently, how many for 1 byte? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Around 12 bytes will be required. Correct. For each character, 1 byte will be required. So what in this compression algorithm will do? First, it will see, can we replace something? Like if we replace this EAA to some other character that is not present in this string. So X is not present in this string, right? So what we will do? We will replace this with X. Then what will happen? This string will become like this: X, A. From here we will give now. And this EAA will be also be replaced by X. Now here how many bytes it will be required? 3, 5, 6, 7, 8, 9, 10. So it got reduced bit. Something else can we replace? Yes. Here
AB.
EAB is there. So from here also we can replace EAB. Then what will happen? So if we replace EAB with Y, so here Y, here also Y. So now how many it is taking? 1, 2, 3, 4, 5, 6. Only 7 bytes it is taking. Also further we can replace this xy with some other value. Like this we can reduce this one, right? So this, like, any question in this, how compression algorithm is working? So this compression algorithm, it is not useful for us. Like, we are not going to use it anywhere. But whatever the logic that that compression was using, we will use to tokenize our sentences, our paragraph. So that is, so we will see how like byte pair encoding tokenizer will work. So consider we have vocabulary like this. Wait, we will see it here. So now what we are seeing byte pair encoding, right? So consider we have our vocabulary like this. We have word 10 times. Then we have word pug, that we have 5 times. Then we have pun, this also we have 12 times. Then we have bun, that we have 4 times. And we have hugs, this we have 5 times. So first thing what it will do, it will split this word, each word into individual characters. So for this, how it will become? So H U G, and how many times this H U G we have? We have 10 times, right? Again, this will be also splitted as P, U, and G. Again, so next step, what it will do? So first thing what we did, we splitted each word or each whatever we have word and our smallest unit whatever we split it into individual characters. So this will be our, we will be working on this one now, this part. So here we will get each individual character as our vocabulary. Our first vocabulary will be, what will be our vocabulary? What are the individual words in this? So first one will be H, U, G, then P we don't have. Again U, M we don't have. Then B we don't have. And that's it. These are the only unique characters. So this will be our first vocabulary. Whatever the unique characters are there, that will become our first vocabulary. Are you getting this? Yes?
Yes, sir.
Yeah. So, and this will be our whatever our data set we have. So then first thing what we will do, whatever the 2 characters that are most frequently occurring, we will combine these 2. Here, which one are most frequently occurring? Here we can see UG, here it is occurring 10 times. Here it is occurring 5 times. And again here 5 times. So 20 times UG occurring together, right? So what we will do, we will combine U and G together. And this U and G we will add to our vocabulary. So here we add UG. Then this one, how it will become? It will become H, UG. Again P, UG. Again, nothing will be changed here. And H, UG comma yes. Then again we will see what are the most frequently occurring words. Here which one are occurring most frequently now?
UN.
Yes. UN here occurring 12 times, here occurring 4 times. So 16 times it is occurring. So what we will do? We will combine these two and then again that UN will be added to our vocabulary list. And then what this will become? This one will be same. This will become UN. Again, this will become UN, H, UG, and yes. And this step we will do again and again. So how many times we will merge this one?
Until and unless we are getting unique words.
Unique words, okay. But consider what will happen when everything is combined together. So we have one sentence like hug, pug, something like this. So this will be combined together also if we combining more times. So we don't have any specific number like this time we have to. This is hyperparameter. So hyperparameter we can tune. Okay. So how much vocabulary size we want? Based on that we will split. So here how vocabulary size is increasing? So first we had our base characters, right? Here we have our base characters, and then how many times of number like merge we make? These two are getting combined, like base character plus merge. That number will become our vocabulary. Are you getting it? So this will be our hyperparameter. So for example, if you want to know, so for GPT has vocabulary size of like 40,478. In that, these 478 are the base characters, like these word, like each characters, then punctuations and characters from different languages, and then they merged it 40k times. 40k merge. So this much vocabulary it became. So did you get it? How large our vocabulary will become? It is depend on how many base characters we have and how many merges we do. And how will we decide these merges? It is hyperparameter. Okay. Any like questions on this byte pair encoding?
No, sir.
Yeah. Okay. Next one, what we have next one? We have word piece. So word piece is almost similar to byte pair encoding. So whatever we did in byte pair encoding, same thing we will do, but just one difference is there. So how we are combining different characters? We are checking their frequency, right? Those characters occur most frequently together. We are combining these two. But here, what we will do? We will check their probability. What I mean by probability, like consider first time we converted U and G, right? So we will check what is the likelihood of these two will occur together. And how we will calculate that likelihood? We will get the probability of UG and then divide it by probability of U plus probability of G. What this will give us? Consider in most of the times U and G are occurring together. then only we will combine. And U are occurring more time, more frequently, but G are also occurring more frequently, and these two are not occurring more frequently. Are you getting how this is happening? So because of that, what will happen? We will first check like combining these character is worth it or not. If we blindly just combine character based on frequency, sometime what will happen in our database, some two words might occur more frequently, but these two words might be get spread. So this is the main difference. What is the main difference? Instead of combining based on frequency, here we will combine based on likelihood of they are occurring together. Did you get it?
Is there any threshold for this probability?
No. So they will calculate whatever the characters are occurring together and what characters has most likelihood. This will be calculated for each character. Those are occurring together, and we will check which one has the most value. Those will be combined first. Then second one will be combined. Get it?
Okay.
Yeah. So this one we can also see like how it is working using BERT tokenizer. BERT tokenizer uses word piece, right? So what we will do, we will see from transformers import BERT. From pre-trained, we will get BERT base uncased. So BERT model has two variants. One is uncased and other one is cased. What is meant by cased and uncased? Anyone knows?
Uncased means it will be in lowercase.
Yes. So uncased means it won't like depend on this one. Our uncased mean it will convert everything into lower, and cased mean alphabetical word like capital word will be treated separately. So if we treating upper word separately, what will happen? Our vocabulary size will increase or decrease?
Increase.
Yes. So what is the main difference? Like uncased, it is converting everything into lower, then only processing. For that, we have only 10,000 tokens. But for case model, where it is treating like case differently, we have more than 30,000 tokens. 30. So by using this tokenizer, we can convert dot tokenize. So we are learning NLP. So how it will tokenize? So here it is tokenized like we. So what it will happen? We are occurring more frequently. Where when the model is trained in that time, then R is also occurring. Yeah, but NLP is not occurring that much frequently. So what it did, it converted N as separately and P as separately. And also you can see it converted this into lower. So if you want to see what is in that vocabulary, what is vocabulary of this one, we can see. So what we will do, we will whatever the vocabulary we have, we will store it into one txt file. So with open as if and for token in tokenizer dot vocab dot keys. So in this tokenizer, we have one file vocab.txt. From that file, we are getting each word by word, and then we are writing into our this vocab.txt. And we want it with new line. We will give new line. So here you can see it. So here first 1000 token will be like this only, unused. What is that? What is use of that? We will see when we are seeing, and some special token will be there. This ANK for unknown, CLA separate, mask. This we will see while we are looking at like BERT. Complete architecture we will see for BERT. That time we will see. So after 1000. Yes. So here our character started. So these are our base vocab, right? Character wise, whatever we did in that. So up to here, like in this, different languages are there also. So here we have our Devanagari script, Bengali, and different language script. After here, words will be started from here. So here. So the was occurring most frequently, then of, and these each word are there. So if we see the length of this one, so it is around 30,000. So this is clear, BERT tokenizer, how it works and what are the different tokenization methods.
येस सर ते आता वापरलं आपण टोकनायझर तर त्यामध्ये ते NLP चं थोडं सिक्वेन्स चेंज झाला तर ते इम्पॉर्टंट राहील का त्या वर्डचा?
हो म्हणजे वेन काय होईल जेव्हा आपण प्रोसेस करणार आहे ना तेव्हा या NL चा वन एक वेक्टर बनेल आणि P चा एक वेक्टर बनेल डिफरंट P चा आणि हे ऑलरेडी ट्रेनिंग डेटा मध्ये असं आहे राईट. त्याच्यामुळे ट्रेनिंग डेटाच्या वेळेस त्याला अंडरस्टँड झालेलं आहे NL आणि P टुगेदर आल्यानंतर काय रिप्रेझेंटेशन झालं पाहिजे.
अच्छा. आणि आपल्याकडे मोठा टेक्स्ट असला ना मग त्यावेळेला कर्स ऑफ डायमेन्शनॅलिटी असं काही वाढतं त्यामुळे म्हटलं.
नाही पण इथे आपण कशामुळे करतोय जर NLP जर सेपरेटली आपण ट्रीट केलो असं प्रत्येक वर्डला करायला गेलो तर काय होणार वोकॅब्युलरी साईज खूप वाढणार. पण ह्याचा थोडस लॉस आहे आपल्याला म्हणजे जर NLP ला आपण टोकनाइज केलं किंवा NL आणि P ला सेपरेटली केलं पण वोकॅब्युलरी साईजचे जो प्रॉब्लेम आहे तो सॉल्व्ह करण्यासाठी मोस्टली आपण हे मेथड यूज करतोय सबवर्ड टोकनायझेशन.
सर या केसमध्ये ते NL ची प्रोबॅबिलिटी जास्त आहे का ऍज कम्पेअर टू NLP?
येस करेक्ट.
जेणेकरून त्यांनी NL. ओके.
म्हणजे ज्या डेटावरती बर्डचा टोकनायझर ट्रेन झालेला आहे त्या डेटावरती.
आणि सर टोकनाइज आता हे स्प्लिट झाल्यानंतर जर समजा त्यांचं मिनिंग चेंज होत असेल तर कसं?
मिनिंग जरी चेंज झालं तरी हे जे हॅश आहेत ना हॅशचा हेच मिनिंग आहे की याचा जो प्रिव्हियस वर्ड आहे त्याच्यासोबत याचं कॉम्बिनेशन आहे. सो हे NL आणि P सेपरेटली काउंट नाही होणार.
ओके.
ते हॅश म्हणजे हे जे आहे ते त्याच्यासाठीच अपेंड केलेले आहेत की ते सेपरेटली ट्रीट नाही झाली पाहिजे.
सो त्या टेक्स्ट फाईल मध्ये 1 ते 1000 पर्यंत काय होतं?
ते अनयूज टोकन होते त्याचं लाईक आणि काही स्पेशल टोकन होते UNK CLS म्हणजे ते काय असते त्यांचे डिफरंट यूज आहेत. आता CLS म्हणजे काय सेंटेन्स एंड ऑफ द सेंटेन्स करण्यासाठी. UNK टोकन काय अननोन जर कुठला अननोन वर्ड आला तर त्याच्या जागी UNK रिप्लेस होतं. हे बर्डच्या वेळेस आपण डिटेलमध्ये बघू प्रत्येक टोकनचा काय यूज आहे.
ओके.
Sir, how to do byte pair encoding?
byte pair encoding also we can do in transformer GPT token using GPT tokenizer. So here for just demo we have seen. So when we will see different models like for GPT during when we will be learning GPT, then we will see how byte pair encoding works. While we are seeing XLM, then we will see how sentence piece is working. Everything we will see. Just for the demo purpose, we have seen here word piece.
Okay.
What will happen here? This one is like this one has small size, but if you try to download a GPT model, it will be heavy model. So it will take some time to download, then processing everything. It will take time. So for that, I have only chosen BERT right now.
सर ते ट्रेनिंग डेटा तुम्ही म्हणला का नाही ट्रेनिंग डेटा म्हणजे ट्रान्सफॉर्मरचा ट्रेनिंग डेटा म्हणताय का
नाही ट्रान्सफॉर्मरचा नाही BERT मॉडेल ट्रेन करण्यासाठी गुगलने जो पण डेटा यूज केलाय तो ट्रेनिंग डेटा जीपीटी मॉडेलसाठी त्यांनी वेबसाईट वगैरे स्क्रॅप केलेले आहेत विकिपीडिया बुक्स डेटा यूज केलेला आहे तो डेटा
ओके
Yes. Any other questions?
No, sir.
Yeah. Then we will move on to our next. This one. This is now text normalization. So what is normalization? When we will do normalization in our classical machine learning, why we do? In deep learning also we will perform normalization. So what is purpose of normalization?
To bring all values in a same scale.
Yes, like some format we are bringing in this scale only. We are trying to reduce the randomness and bringing everything together to some specific standard or something, right? And it will help to reduce amount like different information that computer going to process. And what will happen because of that? Efficiency of model will increase. For that, we need to normalize this, normalize our text. So for normalization, we have different methods. Like one is lower casing, then removing punctuations, then what we will do again? Stop words we will remove. Yes.
Handle accenture character, contraction mapping character.
Yes,
HTML
contractions, then HTML tags, then again
URLs.
emoji
yes, emoji we will handling emojis, then removing URLs. Sometime we will be doing like stemming and lemmatization.
Accented characters.
Yes.
Autocorrect library, in that we can make correct spell.
Yes, spell check. We can spell check also. Okay, and also some other method we will do. So what we will do, we will see now like what is use of like how we will do each one by one we will see. So first we will see lower casing. So lower casing is nothing but we are just converting every word into lowercase. So before we saw, if we don't convert text into lowercase, what will happen? Our vocabulary size will become too much bigger. So there, this, the, and this, the will be treated differently. But we want these both to be treated equally, right? So for that purpose, we will convert into lower. So this is simple thing we can do. Dot lower string method. If you do, everything will be converted into lower. Then next thing we will see removal of punctuation. So for this removal of punctuation, in string method we have punctuations. Import string dot so these are all the punctuations that we can remove. So here we will give into one variable. And simply we have consider we have one text. And what will be the text? Something we have given here. So now what we'll do, we will try to remove punctuation from this text. For that we can use you know that translate function from text dot and then make trans. Here we want to remove comma, we want to remove comma with punct punct. So here each punctuation is removed. So you are getting how this code is working. Yes.
No,
Yes,
sir.
sir,
Can
yes,
you please repeat?
Yes. So these are the methods in inbuilt method for strings, translate and make trans. So what this make trans will do, it will convert into maps. So consider this one, like one text we got here. Something we got this one. So what we want to convert, like change something in this. So here we have yes. Consider we have this yes. We want this h to change to another word. So what we will do? First we will create table. So what is table? Str dot make trans, and in there we will give what we want to change. We want to change yes to, consider we want to change it to r, and then we will use this table txt dot translate table. So here what is happening? So do you remember how replace method work? Dot replace in strings.
Yes.
There what we will do, we can give like one dictionary, key and value. So all the key will be replaced with value, right? Here also this translate method will do the same thing, but only difference is if we go like text like character by character, it will take some time. So but this make trans, it will create the tables, but only difference between that dictionary and this table is it will convert into ASCII values, so that processing will be faster. And while replace will take some more time, here it will take less time. Here R is replaced, but if we saw the table, you can see we have given yes and R, right? So they are converted into their ASCII values. So now did you get it? Here what is happening? What is happening? We are first creating this table make trans using for this punctuation, and we are telling him we want to replace it with empty string, and we are giving it to text. Now get it?
Yes, sir. Yeah.
So next we will see removing stop words. So what are the stop words? Anyone has any idea?
The word which.
and
Word corpus.
Yes.
This word occurs frequently in languages.
Yes. The words like the, in, they are occurring more frequently, but they are not contributing significantly to the meaning of that particular sentence, right? We have like the table or the laptop. Instead, if you remove that the, it won't much affect like the meaning of that sentence. So words that are occurring most frequently, but they are not contributing to meaning significantly, those words are called stop words. So from NLTK we will here and so which stop words we want? We want stop words from English language. Stop words is not okay.
Not word. Stop word, dot word.
Yes, yes. So we have to download these stop words from NLTK. So now we can see if we print yes. So these are all the stop words in the English language. So this stop word like NLTK from corpus support different languages. That languages also we can use. Like if you want to see print dot yep. So here we will get FIEL FI okay. EL file IDs FILE and IDs. So here we will get languages. Here we can see Bengali, we have English, Finnish, French, German. So Hindi we don't have, but we have something English. Like on chat or social media, we'll mostly be using English, right? So if we see what are the stop words in English language. So Adi, Aaj, Aap, Aapne, Ata, Aati, Aya. These are all the stop words like anyone, anywhere. So if you are processing Hindi like Indian social media data, that time you can use these English stop words. Get it? Yeah. So we will see how we can remove stop words now. So here before we have one sentence or not. Okay, we will get new sentence. Learning, then the something we will give something randomly this. So these are our consider these are our words. So what we will do, we will simply iterate over it and we will check if this is not present in stop words, then we will convert it. So we can use list compression, right? So word
Yes.
for text dot split if word not in else expected else. Okay, for word word for word
Or
word
word in
yes word for word in, like this it will work. Okay, so here we can see learning the is removed and this is removed, so stop words are removed. So if you want this to get into sentence again, we can simply use dot join method. So what dot join will do?
it will convert
Convert the list into string.
Here we have to give to space. So here now our stop words removed, right? So for stop word removing, only NLTK is not option. Like for every whatever the steps we are seeing, for them there are different options. Gensim library is there, Spacey library is there, and sometimes Keras libraries will also support. But only for stop word removing, we will see different like demos of Gensim library, Spacey library. And for other option, if you want, you can explore, but it is not necessary. If you know one library, that is NLTK or any other library, that is enough. But just to see, we can perform this with different library. Here we will see. So how we will do it in Gensim library. From Gensim dot there is one function or method called remove stop words. And what we can do, we can simply give our text to this method. So according to them, something is also stop word. So they remove that one. Like they might have different like this one stop words. So again, we will see how to work in Spacey. So we can import Spacey. Then we have to create one object. For anything you are doing in Spacey, first you have to create this object. Then only you can process. So we will convert this into some documentation using this object to text, and then same thing we will do. Like we will get one list and we will give like this token dot text for token in doc if token dot is NER project. We will see how to fine tune using spaCy. These all things we will see. So now stemming and lemmatization. So what is stemming? Can anyone tell?
Converting word into
To mean root.
Yes. So stemming, like if you see this word only stemming, it is derived from the word stem, right? So we want to convert whatever the derived words are there, we want to convert them into their root form. So while stemming, two problems you might face. One is overstemming and second is understemming. What is overstemming and understemming? Can anyone tell? So in overstemming, what will happen? Like we will do stem over, like two or more unrelated word will result in same stem. Like two or more unrelated words result in same stem. Like there is one stemmer, like Lancaster stemmer. If we do with news and newer, these two, it will convert into both word, it will convert into new. So is it correct? These both word are same.
No.
No. So this is the problem of overstemming. What is happening in overstemming? Two or more unrelated word result into same stem. And what is understemming? It is opposite. Now can you tell? So when it is occur, when two or more same, like two or more related word result in different stem. Different stem. So this you might get asked in interviews, like what is overstemming and understemming, how we can handle like this. So for stemming, they have different algorithms, like different rules they have written. If you see in NLTK library only, there are 7-8 stemmers, but today we will see only 3. Those are the most important stemmers. One is Porter stemmer. Then we have snowball stemmer. Snowball stemmer. And third one is Lancaster. These 3 stemmers we will see today. So for the Porter stemmer, what we'll do from nltk.stem Porter stemmer. So same we will do with snowball and Lancaster also. From snowball stemmer. And again, same thing we'll do with Lancaster stemmer. So what are the difference between these stemmer we will see? So Porter stemmer and snowball stemmer. these two are developed by same person and they work almost similar. Only difference is Porter Stemmer only support English language, but Snowball Stemmer will support different languages. So for supporting different languages, that creator of Porter Stemmer, he created Snowball Stemmer. And this Lancaster Stemmer, it is like aggressive stemmer. Iteratively it will stem. So most sometime what will happen, it will result in overstemming. So with different words, how this stemmer will give different result we will see. But before that, we can see how many languages are supported by this Snowball Stemmer languages. So these are the languages supported by Snowball Stemmer. So what is difference between Porter and Stemmer? Porter only support English language, but Snowball support multiple languages. And what is Lancaster Stemmer?
Aggressive.
Yes, it will do aggressive stemming, might result in overstemming. So now we will create object for each one of them and we will see how they are giving result on different stemmer. So first we will create Porter Stemmer. Porter. We will get this. And for Snowball, for Snowball, we will get Snowball English. And here we have to give what is the language we are using. Here we are using English. And then Lancaster Stemmer is also same. So these all three stemmers are now. So for Snowball stemmer, we have to just one thing we have to do first dot stem, and Porter Stemmer we can directly do. Porter Stemmer dot stem here also, and for Lancaster Stemmer same thing we will do. So here what we will do, we will give any word. First word we will see relativity. How each one is like converting relativity. Okay, so what we will do, we will print. So we will be able to see. Porter Stemmer. Same thing we will do here also. So now we will print. So how it is happening now, you can see Porter stemmer. Wait, here we will give something like this. Now, Porter stemmer converting relativity into only REL. So everything it is removing. So Lancaster stemmer is same, but Snowball stemmer relate it is converting. So now we will see this one for word. Word mice. So these two stemmer are not doing anything, but since we see Lancaster stemmer is like aggressive, what it is doing, it is converting mice to MIC, mic, right? Then we will see for maximum. Maximum. So these two stemmer here also not converting, but Lancaster stemmer converting into maxim. So some other words also we can see like private. So again, what is happening? Do we want to remove this E? No, right? It is important, but still they are working on some rule. Every stemmer is removing E, and this one it is making prive, something else. Also, we will see for what it will happen for propose. Here also that E will be removed, right? Also, we will see some other examples such as wander. So for wander also, this wander and wand is completely different, but still it is converting. Here overstemming is happening. Again, we will see news. Here again the same thing it is here happening. Okay. So here I have one image. It will show like what exactly stemming will do. So it is only to remember how stemming is working. What stemming will do: connect, connecting, connecting, connections, connects, everything it will convert into connect. So someone now tell me what is the definition of stemming and what is the difference between these three stemmer? Yes.
Stemming is a process of reducing the word to their best form. And
Yes.
the difference between these three stemmers are Porter stemmer supports only English language, then Snowball supports multiple language, and Lancaster stemmer is a extensive stemmer, or forcefully it stems.
Yes, correct. Okay. So any doubt in this stemming and all the stemmers?
Actually, how it works at the back end?
Like yes. They have created one algorithm. They have some rules. Based on that rules, it will work. So we can see that code if you want to, but consider only they have some rules. Based on that rules, it is doing. For Porter stemmer, they have some rule. Snowball stemmer, they have some other rule. And this also, they have some rules.
Okay.
So here we saw that what is happening for this propose, also for private. It is what happening, sometime it is overstemming happening, sometime understemming is happening, but we are not able to get like root word. Sometime they converting word into like that even is not word, like here we can see propose or the private something it is created, that is not even a word. So how we can say that it is a stem? So for that, to solve that problem, lemmatization comes in. So what lemmatization it will do? So what is the difference between stemming and lemmatization? Can someone tell quickly?
Lemmatization convert to the dictionary form.
Lemmatization, which will make word as a root word, but stemming, it will just try to means prune that word. Means try to make a root word, but it will not consider actual meaning of that word.
Yes. So lemmatization will try to convert word or try to map that word to actual word. It should be actual word. So in stemming, that word root word we are converting is called a stem, and lemmatization, that word called lemma. So for that, this WordNet dictionary we will use. So using this, that WordNet, we can do lemmatization. So what will happen? It will first check whatever that base word we are converting, that is actual word or not. Based on that, it will convert. So we can see from so we saw that for word private and propose, it was not working quite good. So now we will see how lemmatize will work on these same words. Here, this one also not working. Okay, here also we downloaded WordNet, right? Okay,
D is missing.
word,
D is
yes,
missing.
spelling is missing. Previously, while stemming, what is happening? It is converting into some non-meaningful word. Now it is converting. So for private also we will see. Correct. Now it is converting into meaningful words. So now what will happen if I convert into? So what will be output?
Run.
So we will see. Why running is coming if we want run? Anyone has any idea?
We have
So
to give, I think, top speech.
He's not going to find the root meaning word in his dictionary. That's why.
no, run is there in main dictionary. Yes, correct. Here we have to give part of speech, like it is verb or noun. So based on that also, that conversion will depends, right? For verb we want to convert differently, for noun we have to convert differently. So if we don't specify, what will happen, it is considering it as a noun. So noun we don't need to like convert into base lemma. So here if we give v, so v for verb we are giving, now it is converted.
Yes.
Yeah. So while converting, we have to remember that we have converting into lemmatization, we have to give its part of speech. So one word we will see, we have stripes. Stripes can be used as noun also and verb also. So here we will convert as a noun and verb. We have to print both. So now, as you can see, for noun it is lemmatizing differently, and for verb it is lemmatizing differently. Did you get it? Any doubt on this lemmatization?
Sir,
Which
आपण
language it supports?
Yes.
Which language limitation supports?
Okay, different languages you want to see.
Hmm.
So I'm not sure which function to use, but we will see first. Is there any language? No. So I will check like which function to use. I'm not aware right now. So language is not also here. Any other questions?
Sir, when we'll use a lemmatization, as we will have a large amount of data, so we'll not have knowledge of each word, whether it is noun or verb. So how will we use that parameter like
Yes.
or in?
So for that purpose, first we have to do part of speech tagging. Yesterday also I told you, part of speech tagging can be used as feature. Like here we can give. So what we will do, first we will check part of speech for each word, and then whatever that tags we are getting, then we will pass it here.
Okay, got it. Thank you.
Sir, in case if our corpus is large, how can we come to know if there is an overstemming or understemming? Do we have to check it manually, or is there any method for it?
No, manually only we have to check. So we know like working of different stemmer. So if we are using Lancaster stemmer, we can say it will do overstemming. Or for this Porter and other snowball stemmer, we know sometime it will remove that E and S. So we have basic idea. Based on that, we will get the understanding. Yes. Any other questions?
सर इंडस्ट्रीमध्ये मोस्ट ऑफ द टाइम कोणता यूज केला जातो त्यापैकी?
Mostly Porter stemmer use केला जातो. बाय डिफॉल्ट ऑलमोस्ट पोर्टर स्टेमरच यूज केला जातो. कुठल्या तरी फक्त स्पेसिफिक गोष्टीसाठी बाकीच्या स्टेमरचा यूज होतो.
Okay.
Yeah. If you don't have any doubt, then we will stop here today. Have a good day.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.